Hello guys, this is Edward from EDEXCEL. Today I'm going to be doing a revision exercise on atomic structure. By the end of this video, you should be able to answer exam questions on atomic structure. In my previous videos, I have explained the concept of atomic structure, and that comprises of models of atom, particles of atom, atomic mass and isotopes, mass spectrometer, electron configuration, and ionization energy. You can check my previous videos for detailed explanation on this concept. So today we are going to look at possible exam questions that comprises of this concept. And before we get started, if you are new to the channel, please subscribe to my channel, like the video. If you have any questions, drop a comment on one of the videos, and don't forget to turn on your notification bell so you get notified whenever a video like this is dropped. Now let's get started. The first question says samples of 4 different substances are analyzed using time of flight mass spectrometry. In each case, the samples are ionized to form ions with a single positive charge. The ions are accelerated to the same kinetic energy. Which sample gives ion with the shortest time of flight? Now, for you to be able to answer this question, you need to understand the concept of mass spectrometer. Now, although I have done the video on this, but I will quickly give a brief description on how a mass spectrometer works. That will help us to answer this question. Okay. So this is a mass spectrometer. Okay, I'm going to use a schematic diagram to explain what is going on inside the mass spectrometer. The first part of the mass spectrometer is called the sample chamber. Okay, the sample chamber. Now this is where the samples are placed, and this is where ionization takes place. And it occurs by, when fast-moving electrons are used to bombard with the sample. That causes electrons to rip off electron from the sample, and the sample becomes positively charged. Okay, they becomes positively charged, and this is called ionization. Okay, now after the sample chamber, the sample then they are attracted towards the negative plate of a component called the accelerator. Now the accelerator contains a positive plate, and the ions which are being positive are attracted towards the accelerator. So this will make the ions to move with a constant kinetic energy. So this basically helps to accelerate the ions, right? Now note that all the ions of the same type are going to have the same amount of kinetic energy. Okay, they're going to accelerate with the same kinetic energy. Now after the accelerator, the ions then move towards the drift chamber. Now at this point, the ions stop accelerating and they start moving on their own velocity. So they are drifting towards the detector. They are drifting towards the detector. All right. Now the idea is this: the lighter ions are going to get to the detector faster than the heavier ions. Okay, so that is the idea. Okay, now the time it takes for the ion to get to the detector is used to determine the mass of the ion. Okay, now at this once the ions get to the detector, they gain electron from the detector and they cause electron to flow. Sorry, they cause current to flow rather. Okay, now the amount of current that flows, okay, when the ions get to detector is used to determine the abundance. Okay, So basically, the ions get to the time it takes for the ion to get to the detector is to get the mass, okay, and the amount of current produced is used to get the abundance, relative abundance. Okay, so that is just the brief concept, all right, of how mass spectrometer works. All right, if you look at this diagram here, you can see we have isotopes of neon. We have neon 20, neon 21, and neon 22. So basically, neon 20 is going to get to detector faster than neon 21, and then followed by neon 22. Okay, the amount of current produced when these isotopes receive electron from this detector will determine the relative abundance. I hope that makes sense. And now let's get back to our question. Okay, so now the question says, which sample gives ion with the shortest time of flight? And remember we said that the time of flight is used to determine the mass of the sample, right? So the lighter the shorter the time of flight, the lighter the mass of the sample. So let's see which of the sample here has the lowest mass. Now this is scandium. This is scandium 45. Okay, and this is a sample of propane. What is the mass of propane? Let's look at mass of propane. This is C3H8 12 times 3, right? Plus 8, and 12 times 3 is 36. 36 plus 8 is 44. All right. Let's look at sample C. This is a sample of ethanol. Okay, C2H5OH, C2H5OH, and that will give us 46. Okay, that will give us 46. Now D is sample of CO2 that is ionized using electron impact. Now CO2 is 12 plus 16 times 2, that is 32. 32. Now we have 44. So now we have 44, 46, 44, and 45. Now, which of them is our correct? Is our right? Is our answer to this question? So if we start by using the elimination method, you can see that this one is not the answer. This one is definitely not the answer. Look at C. C is 46 is higher. Now we have two 44. Now how do we know which of them is the correct answer? If you look at the options properly, it said a sample of propane that is ionized using electrospray ionization. Now this is the key point here. Now this one says a sample of CO2 that is ionized using electron impact ionization, and the type of mass spectrometer that we are discussing, or that is in your curriculum, is electron impact ionization. There are different types of mass spectrometer. We have electrospray and we have electron impact. But in this curriculum, your curriculum, you are dealing with you are dealing with electron impact ionization. So the answer will be D. Okay. So let's look at another question. So it says, which isotope has 2 more protons and 3 more neutrons than an atom of cadmium 112? Cadmium, okay, 112. Now, isotopes basically are atoms that has the same number of protons but different number of neutrons, okay, or you can say there are atoms that have the same atomic number but different mass number. Okay, because basically the proton plus the neutron is what makes up the mass number. All right, So now we have cadmium 112. If you add 2 more protons and 3 more neutrons to cadmium 112, we have an isotope of X that is 112 plus 5, that will be 117, right? 117. Okay, now what is the atomic mass, atomic number of cadmium? What is the number of proton of cadmium? Now cadmium is having a proton of 48. So if you add 2 more protons to the 48, it becomes 50. So our new isotope is going to have 50 protons and 117 mass number. And what is that option here? Is 10. Our answer is C, 1050. Okay, with mass number of 117. All right. Okay, so let's look at another question. So which equation shows process that occurs during the second ionization of magnesium? This question is under ionization energy, and first you need to understand the concept of this of ionization energy. This is the energy required to remove an electron from an atom in its gaseous state. Okay, let's say for example magnesium, right? Magnesium in its gaseous state, okay, an atom is removed from here to give us an electron is removed to give us a magnesium ion still in its gaseous state. All right, now the energy required to remove this electron is known as the ionization energy. All right, and the equation, this is called the ionization equation. All right, now we can have what they call a successive ionization equation, or yeah, so that's when you further remove electron from an atom. Okay, we have, it's called a successive ionization equation. Now for example, now this is called the first ionization equation. Okay, and this energy required here is called the first ionization energy, right? Now the energy to remove electrons from this magnesium ion is called the second ionization energy, and the equation will be called second ionization equation as well. All right, so now for the second, we're going to have magnesium ion in its gaseous state. Okay, an electron being removed from this magnesium ion to give us magnesium 2 plus, still in its gaseous state, then an electron. Okay, so this is called second ionization equation, and the energy required is known as second ionization energy. So you can have third as well. And for third, you're going to have magnesium, okay, 2 plus. You are removing an electron from this magnesium 2 plus ion, right, to give us magnesium 3 plus, an electron. Now they are still in their gaseous state. Okay, this is called the third. The energy required to do this is called third ionization energy, and the equation is called third ionization equation, right? So now I'm going to leave you with a clue on how to answer question based on equations, that is first ionization, second or third. It's easy, right? So now first look at the right side. Okay, if you're asked to give to show which of them is the second ionization energy, look at the right side. The one that has plus 2 shows that this is the second ionization energy. If it's plus 3, it shows that this is the third ionization equation rather. Okay, all right, so now let's look at the options here. This one has plus 1 on the right side, so this is the first ionization equation, and that is not what the question wants. Now number 2, this has sorry, option B rather, this has +2 on the right side, which is fine, but look at the left side. The left side says magnesium atom. This should be a magnesium ion. So this is wrong. All right. Now let's look at option D. Option D says magnesium 3 plus. 3 plus shows that it's a third ionization equation. All right. Now option C says has +2 on the right side and +1 on the left side, and check, they are both in gaseous state, right? So this is our correct answer. That is for the second ionization equation. Which atom has the greatest number of unpaired electrons? And this question has to do with electron configuration. First, we need to understand what electron configuration is all about. This is basically the arrangement of electrons in shells, okay, in shells of an atom. And shells have what they call the orbit or the orbitals, okay, and we have the, inside the shell we have the s orbital, we have the p orbital, the d orbital, and f orbital. So all these orbitals are found in the shell of an atom, right? And each of these orbital has maximum number of electrons that they can hold, okay? S can hold maximum of 2 electrons, P maximum of 6 electrons, D maximum of 10 electrons, F maximum of 14 electrons. And we have different levels of, we have different energy levels or shells, okay? Now each of these energy levels have the particular orbitals that is found in them, right? Now the first energy level, okay, the first energy level has one s orbital, okay, that is s orbital, so we call it one s orbital, right? Now the second energy level has s orbital, 2s orbital, and 2p orbitals. The third energy level has 3s orbital, 3p orbital, 3d orbitals, and the fourth energy level has 4s orbitals, 4p orbitals, 4d, and 4f. And we know that each of these orbitals have maximum of electrons that they can contain, right? Right, so let's have, here we have 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, and 4f14. Okay, so now there are rules involved in writing the electron configuration, and one of the rules says that the first energy levels are filled first. Okay, so this is the first energy level, so you're going to take the first energy level first. Okay, that is the lowest energy level before you fill to the highest energy level. So basically, if you're going to fill right to electron configuration, you are going to go this way. You're going to write it this way. So you start with 1s2, 2s2, 2p6 and 3s2, 3p6 and 4s2, 3d10, 4p6, then 4d10, and finally 4f14. So if you want to fill your electrons, you fill it in this in this way, okay, levels of energy, right? So now let us write our electron configuration of these elements here. Then from there we can find out which of them has number of unpaired electrons. The first one is phosphorus, okay, first one is phosphorus. Let us write the configuration of phosphorus. So I'm going to clean this. Okay, so phosphorus is 15. Okay, phosphorus is 15. It has 15 atomic number. All right, so The first one will be 1s2, 2s2, 2p6. Then we have 3s2, 3s2, sorry, 3s2. Then how many electrons do you have now? How many total electrons do you have now? We have 4, 10, 12. It remains 3 electrons. So after 3s, what is the next thing? The next one is 3p. So we have 3p3, right? So the last orbital here is 3p3. Now, so let us fill in this 3p3 into its subshells. Okay. Now take note, S subshell has only S orbital rather has only one subshell. P orbital has 3 subshells. Okay, and D orbital has 5 subshells. 1, 2, 3, 4, 5. Then F orbital has 7 subshells. Okay, so just like the way we did the rest of them. All right, so let's continue here. So we have 3p3. Let us read the subshell of 3p3. So we have these. So according to the rules, okay, involved in writing electron configuration, it says that each subshells are filled with electron first before they are paired. All right. So now this 3p3, you have 1 electron up spin. Okay. And if you're using AQA specification, you can use this as your spin, your up spin, and this as your down spin. Okay. All right. So now this is the 3p3 orbitals of phosphorus. As you can see here, it's having 1, 2, 3, 3 unpaired electrons. So let's take note of that. 3. Now let's look at vanadium. So vanadium is 23. Okay, and we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now let's count how many electrons you have now. This is 10, 12, 18, 20, right? And we have 3 more electrons. After 4s2, we have 3d. Then the d will take 3 electrons. Okay. Now I'm going to use this opportunity to teach you or to explain what they call shorthand configuration. Okay. Now if you look at this from here to here, this is 10, right? From here to here is 10, and from here to here is 10. So this is basically 18. From here to here is 18, if that's correct, right? Now, which of the atom has configuration of 18? If you check a periodic table, the atom is called argon, right? So you can always use argon to represent this part of the configuration. So we now have argon in brackets, then you write the remaining configuration, 4s2, 3d3. This is how to write shorthand configuration. Okay, so now the last orbital of vanadium has 3 orbitals, 3d orbital, 3d3, right? So let us fill in the subshell of the d orbitals. D orbital has 5 subshells, so we have this 1, 2, 3, 4, 5. Okay. Now let's put in the electrons. You have to follow the rules, right? So first of all, you feed in the electrons one after the other before pairing. We have 3 electrons that you want to fit in. So we have 1, 2, 3. So there is no more electrons. We have 3 unpaired electrons. So Vanadium also has 3 unpaired electrons. Now let's look at iron. How many unpaired electrons do we have in iron? Right. So let's write the electron configuration of this ion, and we're also going to use the shorthand notation to write it. So we have argon, which has taken 18 electrons. So the next one will be the 4s2 and 3d6. So that makes it 26. So the last orbital in ion configuration is 3d6. Let us fill in the subshell of 3d. We say D has 5 subshells, right? So we have 5 subshells. Okay, 1, 2, 3, 4, then 5. Okay, and so let's fill in the orbital. Let's fill in the electrons. The first, it has sorry, 6. This is 3d6, right? So it has 6 electrons. So the rule says you have to fill in all the orbitals first, right? With single electrons. The up spin 1, 2, 3, 4, 5. Now it remains 1 electron. Then you pair this one down spin, making 6. So you have 1 paired electrons and 1, 2, 3, 4, 4 unpaired electrons. So iron has 4 unpaired electrons. Okay, so now let's look at copper. So copper has 29 electrons, right? Using the shorthand rules or method, we have argon, then we have 4s2, right? Then 3d9. Now this is the expected configuration of copper. However, there is an exception. Okay, there is an exception to the rules in writing configuration of some elements, and that involve copper. Now the exception is this. As you can see here, that the 3d the d orbital has 9 electrons. Okay, so it's unstable. All right, in a nutshell, most of these orbitals want to be stable. They strive for stability, and for d orbital to be stable, it's either it has a half-filled orbital, or a completely filled d orbital. Okay, it's either it has a half-filled d orbital or a completely filled d orbital. Now here it has just 9 electrons, right? And it remains 1 electron for it to be completely filled. So what happens is this: 1 electron from s orbital will move over to the d orbital, and that will make it 3d10. So in a reality, the real configuration of copper then becomes the argon 4s1 3d10. So this is the configuration of copper. All right, now copper has 3d10. So let us draw the subshell of 3d10 and then fill in the electrons. D has 5 subshells, so we have 5 subshells. 1, 2, 3, 4, 5. Okay, so let us fill in the electrons using the rules. First of all, you fill in the electrons 1, 2, 3, 4, 5. So then it remains 5. Then you pair them. 6, 7, 8, 9, 10. So how many unpaired electrons do you have here? 0. So copper has 0 unpaired electron. Now from our options here, which of them is having the greatest number of unpaired electrons? Our answer is, so that is it. Now let me reiterate this particular concept here that involves the exception to the rules of filling electron configuration. Now if the atom, the last orbital, is having 9 electrons or 4 electrons, okay, they are highly unstable, so they are likely going to collect 1 electron from the lower orbital, which is the 4s. If it's 4d4 and then 4s2, so it's going to collect 1 electron from here to become 4s1 and add it to this, and becomes um, um, 3d5. Okay, so also the same thing, if it is just like in copper, if it is 9, it's going to collect 1 electron from the 4s to make it 10, so for it to be stable. So basically they strive for stability. All right, so let's look at the next question.